All right, welcome to computer graphics. So just a quick note that I am going to, instead of doing an in-class exam, I would like to do a take-home exam, but I'll just gauge your interest in doing that. It would make sense because one of the members is remote, so it's kind of, I think would be more practical to do a take-home exam instead of a in-class exam. Any concerns about that?
No concerns.
Okay. I know that the typically what ends up happening is you think, oh great, it's a take-home exam. This means it's going to be 10 times as hard as anything we would have had in class. But on the other hand, I think if I can make the test more of a, how do you solve a particular problem rather than just regurgitate something, I think maybe the learning is better because you're able to apply principles to what you're learning. So, and I will make sure that there's no, no homeworks or anything due on this weekend. And we'll just say they just do on Friday. So that's what we'll go ahead and do then. All right, so so that being said, on Wednesday, I'll go ahead and do a review, and then we can make the class shorter, so it gives you a little extra time to do the exam on your own. So let's see here. Some of the material obviously is based on the book. So in particular, if you're like, I want to study now, the chapters that we're really focusing are chapter 3, which is the graphics processing unit. So understanding how the graphics card is working. Chapter 4, which is all about transformations. We talked a lot about matrix math, vector math, quaternions, and chapter 4 is basically all about that. And then chapter 5, which is shading basics. We've been going over shading the last few days, although we have been talking about some what I call deep rendering topics. You know, we're concerned about BRDFs and so on. I'm not really going to be asking about content that we have been talking about on Friday or today on the exam, okay? That'll be more content that will be on the final exam, just because there's some more, we want to kind of deep dive some more in the advanced rendering, okay? Anybody have any questions so far? Yes?
So if you're giving it this Wednesday, when's it? Wednesday night? Or?
It's going to be due Friday at midnight. So that'll give you a couple of days to think about the answers, and it's not going to be a test that takes you 8 hours. I remember I took Introduction to Differential Equations, and that's one of those like life-changing classes where you take it and you're like, oh, now I know all the stuff I can use calculus for, and that's, you know, to use it with differential equations. So I was hooked on differential equations, so I decided I would take the next class, which is Introduction to Ordinary Differential Equations. And I had a amazing instructor. His name was Dr. Chakravarti. And he could get up there on the chalkboard and he just explain everything in the book in a way that you like felt that you understood every single thing that he said. Well, then we got our midterm exam, and me and my friend sat down one night, and it took us like 8 to 10 hours because just proving some of these, you realize how little you knew. But ironically, at the end of that class, you know, you felt like your brain had like grew an extra size larger because you had taken it, because it was so difficult. And this content can be difficult, but I'm not going to make what an 8-hour exam where you get in there and you're just like, what did I get myself into? But anyways, that's my take-home exam story, which I look back and I appreciated the exam, but it was whoa, I just was not prepared for that. And it was only like a couple of questions, but each question took hours to get, it kind of forced yourself to kind of internalize what you had been learning. So it was good. Okay. So today we're going to spend some time on shading, and towards the end I wanted to I want to go back, and we'll talk more about transformations later if we have time, but we haven't really talked about the per fragment operations that you may have seen in the shading pipelines. That's essentially the part of the engine where it says Z buffering. How do you determine whether one object's in front of the other or not? So we haven't really gone over those particular topics, so I'm not going to ask about details on those, although I will talk about the pipeline. Okay, so let's get into shading part 3. And I think my mouse died. Well, I don't think it died. It just is refusing to connect. All right, so we have talked about, last week we spent a lot of time talking about what's rasterization, what are Uber shaders, what are G buffers, how do you make the G buffer. We spent a lot of time trying to get all the angles right. Because if you don't get the angles right, then you're just going to be feeding garbage. You get garbage in, garbage out. And so we spent a lot of time trying to get the angles right. The angles, N, the normal, that's fairly straightforward. That's the direction the polygon is facing. Or it's the directions the vertices are facing, and then we just interpolate the normal across the polygon. And then if we want to, we could do bump mapping, which is perturbing the normal so that we use a texture map to say, no, this is actually how the normal should face. But we haven't talked in depth of how do you do bump mapping. So for now, we just want to make sure we have the normal. Then we have the light direction L, which is the point from the surface X. So we'll call the fragment X. That's its world position. And the normal just says what direction is it going in. So L is the direction from point X to the light source. And then we have another direction V. Sometimes you'll see E used for eye position or view position. So V is I've been using V a lot lately. So anyways, you have V, which is the direction from X to the viewer, or the other, more generically, it's the other surface that the light is going. So it's the direction that the light is heading towards. Then you got H, which is the direction right between L and V. And so in order to get that direction, we just use our good old linear algebra concept that if you add two vectors together, you get the vector that points right in between them. Okay? And then what happens if we subtract two vectors? What direction does that vector point to? The endpoints. So you get the endpoints, which makes sense because if the vectors were 2 points in space and you subtracted them, you'd end up getting the direction from one point to the other. Okay, so the difference between a point in space and a vector, though, is that a vector always starts at the origin, and points represent an actual location. So it's very easy to confuse vectors as points because we use X, Y, Z, but the principle is the same. Okay, so we have the half angle vector, which we add L and V together, and then we just normalize that. So here's I guess, pop quiz question. What is the difference then between the half angle, so L dot H and V dot H? So what is the difference between the dot product of the viewer with the half angle and the light direction in the half angle?
The half angle between the light would be the degree that the light is hitting the surface at.
No, overthinking it just a little bit. So we want to find out how many degrees, right? The dot product represents the cosine of the angle. So the dot product between V and H and L and H. What's the difference between those two dot products? If H is the sum of L and V together. What is the difference of those two angles? Losing something. Let's go ahead and draw. We have V and L, and we got the half angle.
Yep.
So what's the difference between this angle and this angle?
Oh.
There you go. There is. That's why it's kind of a tricky question, because you're like, okay, if I'm going to take the dot product between L and H and the dot product between V and H. They're the exact same number, okay? Because H represents the in-between angle, and we're working with two unit vectors, so it's going to point right there in the middle. I say that because, okay, clear that. I say that because sometimes you'll see a calculation that says, oh yeah, we need V dot H. And you're thinking, okay, I need to calculate V dot H. Well, if you already have L dot H or vice versa, you don't need to calculate anything else. You already have the value, okay? So recognizing that when we use dot products, we're really interested in what is the angle between two vectors, okay? And most of the time, what we want to do with that angle is calculate the cosine. That's why the dot product is so useful, because we get the cosine if we do the dot product of two unit vectors. Okay, so that was a kind of a pop quiz, make you think about, okay, what can you do with all these tools that we're learning about? All right, so now we have, we're going to talk about different light paths, tone mapping, and we're actually going to talk about render to texture image filters. Well, maybe we might. Okay, so just by way of review, we were talking about our surface point X here at the origin, and we have two vectors coming. One's the omega I, that's the light direction. Omega O is the outgoing light direction. You'll notice that these two vectors, if we were to project them onto this plane, they don't have to be straight. Okay, they can be at odd angles with each other. All right. Sometimes when you draw this two-dimensionally all day long, you just have the sense that the L is going that way. But most of the time, L hits the surface, and you expect L to scatter in several different directions. However, we're just interested, okay, if it is scattering in different directions, how much of that is then going to the viewer? All right. So it's and then your half angle here tells you essentially what is the angle where you would expect to get maximum reflectance, all right, or the direction the highlights would go in. Okay, so we have the rendering equation here. Excuse me. All right, so we have 6 parts here. This is important to remember. So we have the total amount of light leaving surface point X. Next, we have the amount of emitted light. So how much is X have some intrinsic light associated with it? Then we have the integral of the reflected light, and the omega, the capital omega, represents the positive hemisphere. Sometimes I've seen S with a little plus superscript next to it, or you'll see the hemisphere with a little plus superscript. Depends on the context. You can normally just assume that that's talking about the hemisphere, all right? And then we have the BRDF, which is F sub r. That's our function of reflectance, and that has a couple of rules associated with it. And then we have how much light is coming in from the direction omega I, and then we have the Lambert's emission law, which is proportional. In other words, the amount of reflected light is proportional to the angle of light and the surface normal. Okay, so then we have Lambertian reflection, where the simplest BRDF is constant. And we have rho over pi. The 1 over pi has to do with the fact that the area of a hemisphere is 2 pi. And when you do the integral, then you have to factor in a normalization to it. Otherwise, you end up having twice as much light coming out. Okay. Then we have 3 rules. BRDFs have to conserve energy. They have to have the same reflection both ways, and they have to be positive. All right. So positivity, Helmholtz, reciprocity, and conservation of energy. That would be the other name to describe it. Okay. And we already talked about this. Although if you need to calculate a reflection vector, it's 2 times the dot product of the vector you're trying to reflect times the normal vector minus the other one. So this is going to connect. You're basically projecting one vector onto the normal, then you multiply that vector by 2 times, and then you get, when you subtract it, then you end up getting the vector that it's reflected. Okay, now, if you're not going to simulate global illumination, then we can conveniently just get rid of the integral, okay? There is a special tool for that called the, maximize this, Kronecker delta. And this is pretty cool function, Kronecker delta, or actually, am I thinking of Dirac delta? Okay, the Dirac delta function. You notice this is a very special function that is 0 everywhere except at 0. Then that's when you get the maximum. That's basically the idea. So you have Paul Dirac. I'll draw a picture of him up there. It's Paul Dirac, smart guy. And so he's doing some physics here in the 20th century. And we go back here, and let me find the little element here that if you had an integral that trying to see where it is. There you go. So if you have an integral, basically, that if you were to integrate the entire surface, then clearly you know that it's 1, but this enables you to get rid of a integral because at that particular point, that's the only time it's ever 1. So over here, you can see that if I were to take this integral of f of x, some function f of x, and this Dirac delta function, then we basically get the function only at value 0. So in other words, if we were to take the integral of this function with omega I as the only source of light, then we could basically just say, well, then the only time this integral is ever valid is at omega I, and hence we can get rid of the integral. Okay, so there are some tools that we can use. The Dirac delta is what enables us to just like pop, there goes the integral, we don't care about it anymore. And that's what we need to use in order to simulate global illumination. Actually, to simulate local illumination. All right, global illumination means you have to consider everything coming in. Local illumination says we already know where the light is and we want to ignore everything else. Okay, so for now we're doing local illumination because it's easier. We'll be doing global illumination starting next week. We're going to start talking a little bit about global illumination. We get into path tracing. Okay, so we were talking about diffuse BRDFs, and we basically said the diffuse reflection is the scattering of light in all directions. All directions. In other words, when doesn't matter what direction it's coming in, it's going to divide the total amount of light evenly in every direction that is reflected. All right. So, do all materials reflect light isotropically? Well, we have to understand what isotropic means. And isotropic and anisotropic is kind of opposites. Iso kind of means the same everywhere, right? The same. And anisotropic means it's not the same everywhere. In other words, you could have some directions that reflect more than others. This is particularly true of things like, say, CD-ROMs. If you ever look at the bottom of CD-ROM and you notice that light, when it reflects, you get these like straight lines coming off it. And that's because the grooves, we have this platter. And so instead of it scattering light evenly, it hits a groove and then it wants to reflect in one direction. So you end up getting these straight lines that show up because of that fact. All right. So, okay, so Lambertian reflection is isotropic. In other words, it doesn't matter what direction the light's coming in, it's going to reflect evenly in every direction. And we were talking about basically if you have Lambertian reflection, you end up getting N.L lighting. Now there's two kinds of diffuse BRDFs we looked at. One was called Or-and-Nair, and the other one was called Disney. All right, and Or-and-Nair kind of gives a dusty appearance to objects because more or less that's what they modeled. They modeled essentially like clay vases and so on. They were trying to get a better idea of what the moon looks like, and that's where that research kind of led. So it's no surprise that Or-and-Nair is what I describe as dusty. And then Disney gives what I call a velvety appearance, and that's because the Disney BRDF is based off measured materials. So what they were doing at Disney, and I think Burley gave a talk in 2012, and he was talking about all this. They have a library of measured materials, and so they basically measured how real materials reflect, and they modeled a diffuse reflection based on the Fresnel reflection on those. And so I think it gives it a velvety appearance. You can get that soft. It's good for things that you expect to have light scattering as they're hitting glancing angles. So this, you know, for the same reason, if you look at somebody's hair, you know, when the light is shining on it, you get this peak of light at a glancing angle, which is not something you get with normal diffuse reflection because the N.L basically goes from 1 to 0. But in reality, when you look at somebody, that light goes from 1 and it might go down, then it goes up again. And so they use the Fresnel to kind of approximate that. Okay, so we have microfacet models. And what we'd like to think of, instead of like a perfectly smooth surface, we might think of the surface as being rough. Okay, so it's not straight, it's rough, but it's rough within reason. So it's not like this huge mountainous change in surface. If that would be better modeled geometrically. All right, so if you were in your 3D modeler, you know, you would model big changes with your 3D modeler, and you can model smaller changes with a texture map, okay, or these BRDFs. So we basically say that the roughness is 0 if they all point to the normal. So if they're all aligned with the normal, then we would say it's 0. And we say roughness is high if they're distributed in every direction. They go up and down. They're all different kinds of angles, okay? And whatever the case is, it's important that their projected area is conserved. And I'll take a look at Heitz's paper in just a second. So going on to specular BRDFs, which use these microfacets, all right? We have 3 functions here, D, F, and G2. And the idea here is that D is the microfacet distribution, F is the Fresnel factor, and G2 is the masking shadowing function. I'm going to skip ahead real quick so I can open this, this link. All right, so this is a paper that I thought was particularly important when I saw it. And this came out in 2014. And he's done some more works with them. I actually met him this year at I3D, and he was working for Unity now. But this was, I think he was working in Europe at the time. Where was he at? In the Alps. So, so to talk about microfacet theory, and this is a pretty good paper. It's actually really long, okay? And this is kind of an idea of what's going on here is you have this idea of projected area. So, you know, maybe the facets pointing this direction is 50%, and maybe the facets going this direction is 10%, and the facets going this way is 40%. And projected area is basically measuring, okay, how much light then comes from facets pointing in that direction, okay? And so that's how we measure radiance on a surface. But it's important that I'm going to show you here what the masking shadowing does. So we have projected area, which obviously is n dot L or n dot V. That's how much is going to leave the surface area. And we have, we'll call it omega M to represent the direction the microfacet happens to be facing. And then we have the projected area of the visible microsurfaces. So in other words, just because if we're looking this outgoing direction, not every part of the surface is going to reflect, right? And so that what happens is if you ignore that, I think it's obvious if you ignore that, then you're going to be reflecting more light than technically you can even see, all right? And so that's why it's important to have the masking shadowing function. So, so in this paper, he describes one common microsurface model, which is called the V cavity model. And V cavities basically describe a surface where you know, the grooves go in certain directions, and you can measure how many of the grooves are, you know, this shape, and how many of the grooves are this shape, and how many of the grooves are this shape. And so going with that, then you can calculate roughly what, you know, the change in brightness that you would get, okay? So he talks about some validation over here. So you have what's called the distribution of visible normals. And this distribution over here means that of all the surface area, right, 30% is going this way, you get another 50% from this direction, another 20% from this one. So it doesn't matter that they're pointing in different directions. We just care about the projected area. And so the main result from that is that if you wanted to verify, let me find the verification here. If you wanted to verify that your BRDF distribution is, I'll go back to the graphic. If your BRDF was physically based, you could actually measure, just like we measured the FR on the hemisphere, we could do the same thing with the distribution of normals, and that should be 1 because the total amount of area is 1, because that's what cosine theta would give you. All right, so skipping down here. All right, there are different kinds of surfaces, and we'll see this a little bit later, where the microsurface could affect, you know, that your choice of representation of the microsurface affects essentially what you'll end up getting out. So if you, technically you could just simulate the actual surface you're looking at, and then you'd get good results, right? Because it actually measures reality. But a lot of times what happens is that we measure things either with the V cavity model. It's an unrealistic model, but we might use the V cavity model, or we might use these uncorrelated surfaces that they just represent, you know, you can almost think of, you know, car paint, metallic car paint, where you might have little flecks in there that are reflecting. And so you want to find out, if you were to back up until you couldn't notice the flakes anymore, then what would the reflection of light be on that surface? Okay, so they spend a lot of time. There's another picture of the V cavity scattering model. And so basically you compute scattering on separate microsurfaces, and then you blend the results together. Okay, there's another masking issue. And then it isn't, you know, one element here is that, you know, if light reflected here and then bounced off another facet inside the microsurface and then bounced to a part that was visible again, that's another aspect to the masking shadowing, because you might have multiple scattering going on between facets. And most of the time we just ignore that, because unless we spend some time doing some analytical work deciding what that model looks like, because it gets expensive. All right. But one of the cool results over here is that if you use the older V cavity BRDF versus the Smith BRDF, and we're going to talk a little bit more about the Smith BRDF, when you measure it against a reference, in other words, you just randomly generate the surface and then measure the actual reflectance that you get, you end up getting a closer match with this Smith version versus the V cavity. Okay, and the V cavity model kind of comes from some older research into electromagnetic scattering on rough surfaces, and Smith kind of came along and derived a new version of that. But it's only been recently that we've actually bothered to utilize it. Now you notice over here these alpha values. That's what we might call like roughness. And so if we have very low roughness, we'd of course expect a very small reflection value over here. And typically though, we max out at roughness equals 1 because we like controls that go from 0 to 1. It's easier to manage. They don't blow out of control. Because if you were to square 1, you get 1. But if you were to square 1.3, you start getting a number that grows bigger and bigger and bigger. And so we like our numbers between 0 and 1. We would call that unit length or something like that. But you notice we start to get, the results aren't too far off. So as you start increasing alpha, you don't get much extra value with these approximations. They're pretty close. Okay. I have to say this guy did a lot of work. This was this is the anisotropic. All right, so anisotropic scattering, basically instead of getting circular patterns, you end up getting elliptical patterns. All right, and so he's trying to generalize this model. Okay, starting to get a little. That's probably good. Okay. So anyways, the masking shadowing function. So we were talking about this microfacet distribution and the masking shadowing function. So that's what they do. One tells us how many facets are pointing in my direction. The other one tells us how much is being masked or shadowed. All right. And so you can see we just multiply those two parameters together. Now, we have the Fresnel function, and that determines transmission or refraction. So how much is going to go through our surface. And so we call it interface. That's the term. And we can use this approximation called Schlick's approximation. And basically, if you're at a glancing angle, they reflect almost 100%, right? So if you're looking at if you're shining a light, you know, the closer you get to the very edge and you're looking at it, the closer you get to maximum light. And the further you start looking at it close up, then the more the material would just go through. So here's an example of that. If I were to go here, I can show off the Fresnel. So here's Fresnel. So remember last time we showed what the direction would be. Yeah, switch presentation mode. We showed what the direction would be if we completely ignored Fresnel, right? And so it was this really brightly colored, you know, because we're just taking the color of the reflection direction, okay? But you notice, you know, as we're at kind of glancing angles, we get the reflection is pretty straightforward until we start looking at things straight on. And that makes sense because if you're looking straight on through a glass mirror, you expect to see the least amount of reflection. So if you've ever been at the zoo or the aquarium and you want to take a picture of something inside the water, you'll notice that you're like, oh, this reflection, I gotta get rid of this reflection. So it's very hard to take a picture at an angle to the glass. You have to like go right up there and take a picture straight through so you get the least amount of reflection. All right. So this is the effect that Fresnel has on our reflection. So you notice at glancing angles, we get pretty much the most amount of reflection that we're going to get. And then if we adjust the index of refraction, so this is 1.5, this is for class. So if we have very near to 1, then you'll see that we get very little transmission when we look at it head on. And if we increase the index of refraction to something more like a diamond, you'll notice that it reflects a lot more light than normal. Okay, so this is why diamonds with a index of 2.4 tend to look very, very reflective. All right, that's just one of the properties. And if you look at most water, it would be like 1.33. So I'll just go 1.35. And so this would have the effect of, if we were trying to draw transparent objects, like draw this on top of like an underwater scene, then we would basically use that to control how much then can you see underneath the water. Okay, so that's how it's done. All right, that is how that is done. So that's Fresnel. So we were kind of talking about Fresnel, the basic idea last time, but this is more or less how you implement it. So this is really simple because typically we use call it theta d, and that's just a measurement of the light, the dot product of the light vector and the half angle vector. All right, this is why I said if you have v dot h, that's the same thing as L dot H. So you can reuse that vector. So it can be very confusing when you're trying to understand this. You're reading and you're like, how come these people use V dot H and then these other people use L dot V and then, or I mean H dot, or they call it cosine theta D, or they'll not be specific about it. And so this becomes confusing when you read it and you're like, how do you calculate these values? Okay, so any questions so far? Okay, I know most of this has been reviewed, but it's helpful to kind of see it again and again and again. So D is the microfacet distribution. This is the main contributor of what makes objects look shiny. Okay, so the Phong distribution, which we took a look at, uses the reflected light vector, and we dot product that with the normal, so it'd be n dot r, not to be confused with the view direction reflected about the normal. We're talking about the light reflected about the normal, and then we raise that to a power. So the exponent can be anywhere from like 1 or technically 0 to, like, we use a number like 10,000, 20,000. And we took a look at the calculation there where you use this, excuse me. You can calculate E by saying, let's make that 2 over alpha squared plus epsilon minus 2. And the effect that this has is making sure that this is always positive, because we're going to divide by alpha squared here. So that would be a problem if it wasn't positive. And this is how we calculate E. So if alpha is very, very low, like 0, so 2 over, like, say 0.0001 is going to be 10,000. So this is how you can get your really high exponent, by having a roughness that's very close to 0. And then if your roughness is 1, then 2 over 1 minus 2 is going to be 0. So this is a way for us to map the value from 0 to 10,000 or 20,000. Whatever epsilon happens to be is going to be the upper limit. And then we have to divide. So we have to make sure that our projected normal is doesn't come out to more than 1 if we were to integrate it. So we have a normalization factor here of 1 over pi times alpha squared. And this is pretty much going to guarantee that this is going to get us basically almost the same result as Phong lighting, but not quite. It's a little bit more accurate this way. And I think blend Phong is good for modeling shiny surfaces, especially when they're more like plastics, or when you're dealing in a you got a budget, a hardware budget, where you can't just calculate some fancy function just because you want to. So this is useful if you need something that's hardware constrained, like your cell phone. Okay, and so this other distribution is called the generalized Trowbridge-Wrights, and we kind of mentioned that with blend Phong and the other ones, we're kind of using a V cavity model. That's kind of the general approach there. This other one is actually, instead of treating the surface as a bunch of V cavities or even just like randomly placed facets, instead what we're doing is with Trowbridge-Wrights, we're saying, well, what if those surfaces were a bunch of little ellipsoids in space? So Trowbridge-Wrights kind of deal with like half ellipsoids, but they have recently they've done some work to kind of figure out what should it be if you had the full ellipsoid thing. And I can't really share results with you right now about that, but it was pretty, I learned about it earlier this year. So Eric Heitz has really been like working on this GGX model. And this is pretty much the de facto, if you want to make good physically based rendering, use GGX. That's basically, the only reason to use blend Phong anymore, like I said, is you have no other choice. So GGX is better. And so this function over here, we still have n.h, but this does a better job of handling it. Now there's an older model called the Beckman distribution, and I don't want to show that one just because it's it's not as nice as it could be. So it's a lot more heavy duty of a function to calculate. Well, this one does it. It's a little simpler to understand, but you can approximate it as you set this value of gamma up to 10. So that's one way of approximating it. And then otherwise we just use a value of 2. So we'll say GGX is 2 and Beckman is approximated with 10. Okay, so so now that we have the distribution, so D, then we want to plug this into the masking shadowing function, which is G2. All right, so there is a G1, but the only difference between G1 and G2 is that we have 1 over 1 plus lambda for one direction. So G2 uses both the incoming direction and the outgoing direction, which makes sense, right? You'd expect that masking or shadowing would apply to the incoming direction, and then in turn, anything that could be reflected would be attenuated by how much could even leave the surface to begin with, okay? So, so for GGX, the Smith function, so that's what this lambda function is, the Smith function. And it was actually kind of funny, the Smith function, so we have Peter Beckman, who is worked for University of Colorado in Boulder, and he was doing work on scattering of electromagnetic surfaces. And he basically, when Cook and Torrance came up with the Cook-Torrance model, they basically utilized Beckman's work, and that's why Beckman's distribution became important for computer graphics. Well, it was funny because in the IEEE journal that this stuff was published in, there was some other gentleman who strongly disagreed with Beckman, and they had this little going back and forth moment in the journals, like, no, you're wrong, no, you're wrong, or you're not using this right, or there was this, and then Smith comes along and kind of says, no, well, here's the real deal, and and then that was it. So it was actually kind of funny to see, like, in the journals as you're researching this, you know, to see the fight that was happening there. And then ultimately this one prevailed, the Smith one, although it was kind of buried for a long time until the last 10 years, basically. So, but most people don't know about Beckman's issue in the journal, because I was like going and trying to find all the different clips and pieces there. But anyways, so over here we have the Smith function, right? And so the Smith function, well, basically, if you're going to calculate G2, it's 1 over 1 plus all of this for the incoming direction plus all of this for the outgoing direction. Okay, so this is why you obviously try not to do this on your phone, right? You know, although that's changing every year. It gets with more computing power. And then the blend Phong function, this is more in line with the Beckman. You use this dot product relating the half angle with, you have the outgoing angle and the incoming angle. This looks wrong. I have to fix that. So that should be omega g dot omega h, omega g dot omega I dot omega h. So they're kind of mirrored, and you just take the minimum. You take the least amount. So you just assume that worst case scenario, all the light's reflected, and then you just take whatever the least amount you would expect to be reflected as the your G2 amount. Okay. All right, a lot of math. Before we start taking a look at light pass, let's take a look at code, because code is interesting. We like to be able to translate our math to code. And we'll start out by taking a look at the results. So let's go over here, make sure I don't have any hidden messages. Okay, so as you know, we have our Disney BRDF over here, and I can adjust this. I can basically adjust the Disney one. So let me zoom in just a little bit. All right, so I can adjust the, this is the one that kind of gives us soft results, right? So if we go down to 0, we get our normal N.Al lighting. And then as we move away, it kind of makes everything look soft. And then the next one is Air, which kind of has a dusty appearance, okay? So we can kind of make things look dusty just by, I guess, changing that value. Okay, so, and then this allows us to see what happens if you do both. So we get the most amount of reflection if we just go straight diffuse, and then we see an attenuation on both sides if we do one or the other, okay? All right, so the first one then is blend Phong. So at this point, we want to make everything look shiny, all right? Because shiny is pretty good. So we can go ahead and adjust our specular color. So I'm going to put this back at 0, so we have no change in our diffuse reflection model. Okay, so this is our. I'm going to see if I can zoom in here just a little bit more. Too much. Come on. That works. Okay. So, so blend Phong, this is what we would consider to be kind of the minimum, and I can kind of move my sun around so we can see exactly what happens. So this is the effect of the blend Phong model, which is it's good. It's a good result, but it doesn't yield the best images yet. Okay. So the next step up is to use GGX, which is the ellipsoid based model. And so if I, oh, I guess if we change the, if we change the amount of reflection over here, then we can see that it basically just smooths out, right? So if it gets, in other words, if the object is pretty rough, you wouldn't expect to see shiny highlights on it. They just kind of look faded out, right? So that's kind of what this model does as we increase that. And then the next model is GGX. So let's add GGX in here. And so GGX looks similar, but it has a different response to it. All right, so let me put something that's kind of shiny. I don't know if I can zoom in anymore. Okay, so if we were to go back and forth between GGX and blend Phong, you know, we can more or less approximate it. But what I want you to notice is that the fall off for the blend Phong tends to be pretty abrupt, and the fall off for GGX tends to be a little smoothed out. So if you were to take a look at the reflection of chrome, for instance, you would not see a very shiny, perfectly circular area. You would expect to see the circular area, but then faded out a little bit around the edge. So it's a little fuzzy. So if we go to GGX, then, and I kind of trying to get the closer one, you'll notice that it fades out a bit more than the other one. I guess it would be, we can change the source code here. That's one of the nice things here. We can change the source code. So when we're looking at, oh, actually that's a good, I could do this. When we're looking at one or the other, we'll just show the specular color. And when we're looking at it all together, so we zoom, go around here. Okay, that looks visible. All right, so let's go in just a little bit more. All right, so this is our, that looks right. So if we were looking at our sun direction coming around, that would be blend Phong, all right? And if we go to GGX, there we go, GGX, you notice that it's a bit more, it spreads out more, okay? And that exactly follows what we saw inside the paper, right? And remember when we looked at the little heat map? Okay, this is exactly why when we turn on one or the other, then we see this spread out, okay, quite a bit more. So this fall off is a lot shorter than this one. And this is actually, when you actually compare what the reference is, this is more accurate, okay? In other words, you don't have quite as big of a loss of energy, all right? So there's the GGX, and then you'll notice we still, as we get to a roughness of 1, it still spreads out. So more or less, it's kind of acting like a diffuse surface, and even the highlights tend to have a good amount of scatter around them. Where if we go to blend Phong, then we don't get quite as I don't know if I'm able to show something quite that small. Okay, but you notice that when we increase the roughness, when GGX was going, it tended to be a lot more surface area. Watch how this opens up. This kind of blooms. All right. This is how it kind of blooms. All right. And you'll notice that when we use GGX, it's a lot brighter. So in other words, when you have blend Phong, you're not even reflecting everything. You're missing out. All right. And so with GGX, we get a better distribution, and you'll notice that the fall off seems a lot more, a little more realistic. This is actually good for metallic objects, right? And that's kind of some of the problem we were having, is that when metallic objects just didn't look very good. They looked plastic, but that was not really what the intention was, okay? So this is, in fact, I think just looking at this, it kind of looks metallic. If it does have that, versus, you know, if I go back to blend Phong, it is not the exact same thing. It looks kind of, I think we have to go just a little bit. The problem is it's just too dark. Like you would expect that there'd be more reflection even on a metal object. And so it just doesn't behave very well. Okay, so let me go back here. Okay, so there's GGX, and this is why it does a lot better. Okay, so there's a little more computation, and I would say that at the intellectual level needed to understand it, you have to put more thinking into it, because the thinking with blends, yeah, you just raise n dot h to the power of whatever, and that's how you get it. Okay, that's very simple. This one requires you to understand how the Fresnel is working, how the microfacets are working, and how the masking shadowing is working all together. You kind of have to understand all of them a little bit better than maybe we would. So then if we go back here to our the bimodal one, where we add the diffuse color back in, then I guess we'll turn the light down. So this is our GGX model, and then this is our blend Phong model. Okay, so this is a much better fall off response. Okay, so that's GGX. Now the one thing we talked about then is the Beckman distribution. Okay, and so we said the Beckman distribution can be approximated by adjusting the gamma. That we raise it to the power of 2, but if we raise it to the power of 10, then you'll notice that we get these really sharp. Oops, let's come on. We get these really sharp fall offs in the same way that we get for blend Phong. So you notice over here we get these really sharp highlights. Well, we can still get the same thing with GGX. If we increase the power, and this is just the fact that if you were to raise, if you were to raise the power of a cosine function, you basically just make it skinnier. All right, so that the only time you get high values is when you're closer to having a small angle between the two, right? Because cosine of 0 is 1, cosine of pi over 2 or 90 degrees is 0. So if you're trying to adjust how much gets reflected, then we can just change this gamma value. So by having this gamma value go out, this is probably one of the real reasons why it looks so good. Okay, is just because we're using the ellipsoid as a model versus to just V cavity model. Okay, so any questions so far? And we haven't even, and I guess we could just see, you know, what's the effect of Fresnel on the reflection. So obviously, if the higher the n, the more it's going to be. Although for a long time, I guess I wasn't thinking very well on how the Fresnel works, because you know, how does Fresnel work for metal then? And metal's like one of those cases that they don't act right because they actually have a complex index of refraction. In other words, you know, you have to use complex numbers to represent what that color is doing. So basically the color that's reflected. But one of the easiest ways to approximate I guess a metal color is just simply say, well, what color of light is reflected? Okay, so if I go over here inside my JavaScript code and I pick a color, so right now I'm picking a color of white, but I could also do, let me get a, I'm gonna grab a gold color. I think I have a function called getColor. So let's change this so that we what's that? So we get a metallic reflection. All right, so if we go back here to GGX, all right, and zoom in, and we change our roughness back up, then we can, I guess we can approximate the, you know, gold just a little bit better. And if you change the gamma, this is the problem, is like it's, you know, it's pretty decent at like saying, you know, what it looks really shiny, right? But this is actually what's interesting is that it's not intuitive, because at first you say, well, what's the reflected color supposed to be like? And so you say, this is a segue into our next section of light pass. Only the light source, nothing else. Okay, and so that's why it's black. Everything's black. Notice that everything's black. So if we were reflecting our colored environment, we would also have to take into account the surrounding light, right? So in order for us to do that, I have to take that reflected color. So remember we had our reflected color over here. Where was it? There's our, I was calculating the Fresnel. Okay, so in order to, if we were going to apply this to our, I guess to our GGX model, we'd have to add it in over here. So, so there's our actual color that we're reflecting, and we also, because we're using fragment.r, I'm going to call this I call this reflection GGX. So we can see the effect of adding in. This is going to be material.cs times specular of, this is our roughness. So we use the M for the roughness, and then this is specular alpha. And so now I need to recalculate these. We need to basically recalculate our light for all these different directions. So I'm going to say that this is equal to our fragment.r vec3 we need to actually get our, this is the color basically that we're going through. This is the incoming light color now, all right? And so we need to also calculate the n.al. So I'm gonna call this r. I'm gonna prefix these by r just to let me know that I'm actually computing this with different light values. So RH, we would have to say that's the same as RL plus our normal, or actually plus our view vector, which if we think about this, our half angle is going to be the normal. Because if we reflect our V vector around the normal, then if we add that resulting vector with the original, what do we get? We get the normal, because halfway between, so I guess going over, you notice here we're going to reflect to V, right? R, this is the direction we're interested in. So if we reflect V about R and we take the half angle of R and V, what do we get? The normal. So technically our half angle is the normal. And so what I'm doing here is, if I just generically apply this formula, then I'm just looking at this, I'm like, wait a minute, this is just the normal. Okay, so there is no half angle. It technically is just the normal. So I'm just going to grab n. And so then when we calculate some of these values like rn.al, this is just going to be n.v, right? Because the light vector. So, but we'll just calculate it here. Max of 0 and RL and n. Okay, so that's just going to be n.v, which we've technically calculated. And then r n.h, what is that going to be? We said that h is normal, so what's n.n? Take the dot product of any vector by itself, and what do you get? No, you get 1. Cosine of 0 is 1, right? Okay, that's easy enough. And then RL.H is going to be, this is L.H, so this is technically V.N again. So, all right. So I'm going to just say this is fragment. I'm already calculating this, so n.v. Okay, and this is the exact same thing. We'll just leave that there for now. Okay, so that should be the reflection color. Let's see if I have any. No doubt I made a mistake. So line 322, I have an extra underscore. Line 319, there's no function that takes, dot. Although that's still just n.v, basically. Okay, so that looks good. I think I was aiming for case 24. Oh, actually, we're the GGX. We were adding it to GGX. Okay, so technically, yeah, we should be getting some reflection here, but the Fresnel is affecting. So we're gonna zoom in. All right. We got to figure out what we're doing wrong over here. We probably have one of the vectors backwards. So it's probably I'd be willing to say it's this one that's not quite right. Let's try that out. GGX. Now we're just getting a bunch of white out.
Looks like the opposite.
Well, no, because it's white. I bet that if I were to go down here and let's we're going to look at tone mapping in just a second, but maybe I meant to calculate. Nope, that's fine. Let's stick an arbitrary constant in here. Try to scale it down and see what happens. That's one way of handling that. Oh, okay. I know what's going on. In this function, I'm making an assumption about the intensity of the light. There's GGX. Okay.
That's not the right case, is it?
What's that?
That's not the right case, is it?
It should be, because I just added it in for GGX. We're adding reflection GGX. And I think these are all technically correct, because n.L is the same as n.V. N.H is just 1, and L.H is just V.N.V. So same directions there. Let me just go up into the specular color and just see what we're doing there. So specular, see over here I'm multiplying Li, which is technically the light intensity. So that's the actual, like, which I think I just have defined as 1 for right now. So that's why this kind of works. We're just saying that the reflected light, where is it? Oh, that is a problem. We're saying that it's dependent on, well, no, I guess that's fine, because if the sun is like going down, so we do have a problem here in terms of we're basically getting no attenuation. Let's see what happens if we got to figure out why we're only getting oh, I guess, yeah, I guess in a way that makes sense. We're getting a perfect mirror reflection, although I would think the Fresnel would have some ability to like tune that down a little bit. Okay. So we might not be calculating this 100%, but I guess it's, I guess I'm curious why it's not getting a gold color. So let's add that back in and just make sure we're multiplying or modulating. There's the reflection color times the surface color. So this is what's reflected. Let me just call this reflection color. Okay, then we have n.v, n.v. Let me just make sure that I'm actually reflecting what's the material.cs. So I'm actually reflecting this color. I think in a way I just have to trust it. Although I was expecting to see it, I was expecting it to look gold. That was what I was intending to do there. Let's just make sure that the only thing I can think of is that when we're let's make sure that this is not getting out of control. I think I have to pass in a vector for those. Oh, nope, I guess that's fine. This tells me is that somewhere along the way, these values are exploding. This is a good debugging exercise. So let's go make sure inside of our ggx function that we're not actually, because our values like G2, for instance, shouldn't be, G2 should never be, it should always be between 0 and 1. All right, and float d equals clamp d ggx n.h between 0 and 1. And our for now should probably be okay. Oh, let's find out what did we do wrong. Line 240. BRDF equals. Semicolon. Okay. There we go. Okay, so somewhere along the line, our ggx function was exploding. So either D was not operating correctly or G was not operating correctly. Okay. This is more what I'm thinking about. Okay, so if we zoom in here, you know, technically if you were in this like really colorful environment, then we would expect the gold, you know, to have this, I guess to have this effect. And that's for now doesn't have too much of an effect to that. So if we have our sun go up and down, then what we have here, I guess, let's go ahead and put our sun up and down again. I mean, the point I was trying to make here is that we have to think about what light paths contribute to why an object looks the way it does. So if you only consider the specular color in the direction from the light source and you ignore the environment, then you're not going to get a realistic result. Okay, that's part of the point. So I would expect that more or less gold, if in an environment where it was surrounded by nothing but color, would have a tendency to look like this. All right, so it's going to attenuate the colors more or less to a gold color. But I have a better demo to show you, which I may have shown you this one already, but I don't remember. And if you do it correctly, then the result that you get, and so this one is basically calculating for now for red, green, and blue, and it's actually using the entire spectrum, I guess the proper way. So that's loading up there. So I have, I'm going to go with the dull finish here, and I'll pick gold. All right, so if you do it the proper way and you have the appropriate reflection value, so I use a nice map that looks like you're outside, then what you end up getting is something that looks just like gold. And the reason why this looks that way is because, as I said, you have this complex index of refraction. So this represents N and this represents K, or kappa. So that would be like your I value. And so in blue, green, and red, what ends up happening is that your reflection values tend to look, there's strong reflection in the red area, to a lesser degree, they have green, and for blue, you have a lot of absorption. So if you were to look on the other side of say, gold plated glasses where the light's transmitting, that's why it would look gold, it would look blue, all right, because most of the blue light's transferring through, okay? So astronaut helmets have that gold layer on top of them. So they're reflecting gold, but if you were to look through them, then they have this blue layer to it. And this is in contrast to something like, say, shot glass, where you notice your red, green, and blue have this really low reflection. That's why on a lake, right, you can see through the water if you're looking straight down. And if you're looking, at glancing angles, you pretty much get max reflection, all right? And for metal, it's not the same thing, because you look at metal and you see a lot of reflection, just strong reflection, okay? So let's go to shot glass over here. So you'll notice that if this was, made out of glass, that, our shininess more or less looks like, you have a combination of the reflection of the surrounding environment, but you also notice that that the diffuse material, in other words, if the bunny was red or the bunny was blue, that would reflect more, because then the light reflects off the internal diffuse color, and that's why it looks the way it does, okay? So metals act very differently, and so I showed you one approximation for doing metal, which is just simply change the reflected color. But as we can see, you need something more advanced to get better results. All right, so and we'll take a look at some of the details on this particular demo in the future. But let's go back over here to our BRDF. Well, actually, let's go to the presentation here and take a look at the light paths. All right, so we would say we might have a main light in the scene, so that could be the sun, or it could be the dominant light. Maybe you put like a lamp up on the ceiling. All right, that's the main source of light, but it's not the only source of light. And typically, what you have, especially if you want to approximate global illumination, I would say on the if you're doing an outside environment, you're going to need to handle the reflection, so the light coming in that's reflected on the surface. Okay, so you need that, and you need irradiance. And irradiance is basically how do you sample the hemisphere around N. And so one approximation to doing that I do in this demo is you can basically turn down the So I have irradiance turned all the way up, but let's turn down the reflections and see the effect of irradiance. So in this one, you just use a very low resolution. You notice that it isn't like a mirror reflection anymore. This is just a low resolution. I just look into bitmaps for a really blurred out version of the environment, and that's how you can approximate the irradiance. So because you're expecting lots of crazy, change in direction here. And if I were to go straight to the reflections, so I turn irradiance down and add reflections in, first of all, I need to turn down my exposure. And you notice that this is, mirroring. So this would be like really polished metal over here, okay? So if it was really polished, what's that?
There's no diffuse at all.
Right, there's almost very little diffuse. Well, it's just strongly reflected. But over here I have, so if I pose this and I do,
Edges are brighter. Is that supposed to be like
what's that?
that? Edges are brighter. But
That's because of the Fresnel effect.
okay.
That means that as I'm getting closer and closer to the edge, I'm getting a huge boost in reflection. And that's because we're looking at Fresnel over here, okay, where you get 1. And so when you're looking at it straight on, you should see the least amount of reflection because technically that would go straight through, okay? So that's one of the things with the Orin Air, we don't have those highlights on the edges, and that's why it tends to look dusty, because dusty objects just look kind of dull. And velvety things tend to have that Fresnel effect in the edge, and so you get that like soft velvety glow on the edge there. All right.
So to get kind of like a cell shaded look, would the approach be to have that curve that approaches 1 as you get to a fully
Right.
tangential surface? Would you just have it like cut up and then go to no reflection, so then you end up with kind of like a black edge around those parts? Or
Well, actually, we'll talk about that now. And we got some time. Okay, so so light paths. I was going to show you the other kind of shading, which is like non-physically based shading, which I don't think. Here's a slide that kind of represents some of the microservice models. So you can like do uncorrelated or Trowbridge writes. So this is what GGX is based off of. So we're modeling a little ellipsoids, tiny ellipsoids that on the whole, that's why we end up getting all that extra reflection is because we don't oversimplify the model. Although it is there is some niceties about using an ellipsoid that has recently just been kind of explored. Okay. Then tone mapping, right? We were just looking at tone mapping because you notice that if I use one light direction, you see very little of it. In other words, irradiance is going to cause what's reflected to go way down. And a perfect reflection, though, is going to be very bright because it's not attenuating it. Okay. I guess we'll talk more about tone mapping on Wednesday, but let's talk a little bit about Gooch shading, which Gooch shading is a, it's I don't have this perfect on here. We can talk about, I guess, in the fragment shader. Right now, I'm just calling, let's see here, Gooch with, it's not really +1, but we're going to go with it. We're gonna make another function called tune. And so the idea behind Gooch shading is that we take the a cool color and a warm color, and then we blend the surface so that it goes between this. We basically modify the surface color so that it blends between the cool version that we would call it. So those are like more blues, and the warm version of the color, which are more yellows, right? So over here, 0.3, 0.3 in red and green is going to give you a dark yellow color. And then over here, 0.55 is going to give us kind of a more equivalent of a blue color. So we're going to be blending between yellow and blue. And so then we take the dot product between the two, and then we scale it. So instead of going from -1 to +1, then we just say that it's all, it goes from 0 to 1, okay? And this is because we care that the objects are facing away from each other as well. So if I was to just return the material color, and we'll have to do this over here. Let's see here.
Instead of going from 0 to 1, it goes from 0.5.
What did I do wrong? Oh, first of all, there's no tune, so let's just. Okay, vec3n, vec3l, return. Okay, so we'll just ignore any color like that. So if we go here to our Gooch shading, you'll notice that instead of having values, you know, if it's 0, technically, then we return just like a low color version of the original one. And if it's positive, then you know, so basically we light objects that are back facing to the light. Okay, so if I were to move the sun around, then you'll see that with Gooch shading, it never completely goes dark on us, right? So that's the one premise on this one. But then we can use the whether it's cool or warm to affect the color. So in other words, if we use T and we say let's take the warm color, and then let's take 1 minus T times the cool color. Oh, now I know why that wasn't. I was like, how come this isn't working? So let's go back here to Gooch. Now you'll notice that we have, if it gets a cool color if it's facing away from the light, and it gets a warm color if it's facing towards the light, right? So this would be lights all the way down, and then so you can see this allows us to basically view our object without having black shadows in it. So we can kind of look at this and say, oh yeah, I know what the shape is on this, all right? And if you have several different colored parts to it, then what'll happen is you can still differentiate what the model looks like, but at the same time get a non-photorealistic rendering effect, okay? So then the other option is to do stepping. Okay, and actually, let me see if this is going to work. I guess the one modification we can make to Gooch shading is to make things shiny. So I don't know if this does that or not. I think I did. That wasn't working 100%. So let's go ahead and try that again. So we can add basically just a shiny version. We can add some. We can make the objects look shiny by adding a little bit of Phong shading to it, and it looks pretty good. So this is one thing you can do with Gooch shading, is then add a little specular highlight to it, and then this gets you a very popular visualization technique. Okay, so this is a modification that they suggested in this book. It looks pretty good to me. We should probably try to get these objects to look different colors so we can experiment more. What time is it? It is 5 o'clock. I guess I could throw together tune shading in just like a minute. This is how easy it is to do tune shading. So we calculate n.al, and we'll go maximum of 0 and the dot product of n and l. And then what you do is, we'll just say, minimally speaking, it's going to be 0.2. And then you can say if n.al is greater than, say, some specification, then we'll say that t equals 0.4. Else, if n dot L is greater than 0.7, then say t equals 0.7, and then else if n dot L is greater than say 0.9, then t equals 1. And so what we're going to do here is step our reflection. We're going to step the reflection so that it's only certain values are accepted. So if I go over here to not implemented, you'll notice that if I were to bring the sun down, that let's zoom in a little bit. Okay. You'll notice that now our values are some fixed. So now we basically make this look like a cartoon by using cell shading, right? So we say, well, we color it with light purple or we color it with dark purple. Okay, and then what you have to do is then you have to say, well, it would be nicer if maybe we're being a little too strict over here. So
Did you have it fully shaded most of the way and then have it cut off?
well, it depends how many bands you want on this. So if we're a little more careful here, then we can give this a little more bands. And this is because the cosine value is not perfectly, let's see here. Let's go ahead and, oh, I know what I'm doing. We never get past that point. We have to go less than. Else t equals. There we go. Now we have more. So this is a case you just have to kind of know where your values are. So okay, so now we got several bands for the shading, and so as we look at this, then you can just adjust them however you want. I'm going to talk about a little bit more sophisticated version of toon shading at a later time, but yeah, that's how you do cartoon shading. That's maybe even easier than Gooch shading, but that's and then you can even apply that to Gooch shading. You just mix and match all the stuff, combine them in different ways. So if I wanted to, I could actually exactly, yeah. So if I were to combine this together, then
That's really cool.
and so now we get so now if your sun's going up and down, then you get a little bit of Phong shading and then like a specular highlight.
That looks really cool.
Just invented it just now. Anyways, so yeah, so on Wednesday we'll go ahead and talk about we'll go ahead and talk about kind of review some of the stuff for the midterm, and then I'll let you guys take it. You have it till Friday, and then that'll be that. There is a possibility I won't be in on Monday, but I will let everybody know if that's the case. And if that's the case, I'll send out a video to watch, probably just because I'm driving back from Anchorage on Sunday night / Monday. But if there's a snowstorm or, I'm not going to like drive into a ditch for you guys. I'll just be honest there. So if it's not safe for me to get back in time, then I will not be here. But I'll assign some alternative video to watch in exchange. All right. So that's it. If you have any questions, feel free to come ask. But yeah, this is fun. I'm having fun putting all this stuff together. So okay, I'm going to end the share, end the meeting.